So we're looking at max and mins of exponential and logarithmic functions. We're going to be working with both local max and mins, but we're going to start by finding local max and mins. And then what we're going to do is just address what would be different if we were given an interval instead of just finding the local max mins if we wanted to find the actual max min on an interval. So 3 questions we're going to roll through. So remember, we're going to find our critical values, which are going to be where the derivative is 0, where the derivative does not exist. Shouldn't write equals, just derivative does not exist. And then if we were on an interval, we'd also include the endpoints of that interval as certain critical values. And then when you're doing local max and mins, remember you have the choice. You can do the second derivative test, where you find the second derivative, you plug in the value, and you see if it's positive or negative. But what we're going to do is we're going to do the first derivative test, because the second derivative test, well, you have to find the second derivative, and it might not actually work at the end of the day. If you get 0, you have to go back and do the first derivative test anyway. And the first derivative test just comes down to making a factor table for the derivative and seeing if the signs change at that critical value to see if it's a max or a min or not. So with that long explanation, we're going to get the derivative of this first function. Again, you can pause the video and work through these and then watch the video after the fact and see if you got them. But derivative of e to the x is e to the x, so derivative of e to the function is e to that function. And then the chain rule says multiply by that function's derivative. So that should be that. We're going to get negative e to the minus x plus 3 e to the minus 3x. And so where we have to do, we have to solve where this thing is 0. And in order to do that, what we have to do is we have to do a common factor. So with the negative exponents, it gets a little bit confusing. Let's say you had something like this. The thing that you would factor out is x to the power of 3, because that's the smallest power in common. Something like that. Similarly, between e to the minus x and e to the minus 3x, the smallest power is e to the minus 3x. It's smaller than minus 1. So I'm going to factor that out. I'm also going to factor out that negative from the first term, because I like to. So with this factored out, I have to think, well, my negative's out front. E to the minus 3x times what would give me e to the minus 1x? Well, I'd end up adding exponents, so e to the positive 2x times e to the minus 3x would give you e to the minus 1. And then since I factored out the negative, this is going to become minus. There's a 3, and since I factored out the e to the minus 3x, it's sitting out front. So this is our derivative. It's a nice exponential function. It exists everywhere. You can plug in any x value to that. You'll never get a problem with that. So we don't have to worry about where the derivative doesn't exist. We just have to worry about where the derivative is 0. And we have it factored. And the first factor is e to the minus 3x equals 0. And we should know that there are no solutions to that. So e to the minus 3x is never going to be 0, because again, an exponential graph never crosses the x-axis. E to any power is never going to give you 0. But this part we can actually get solutions from. So we get e to the 2x minus 3 equals 0. So e to the 2x equals 3. Now the trick to get the x out of the exponent is to take a logarithm of both sides. And since our base is e, we might as well take the natural logarithm. And what that does is the 2x floats down in front, and then you get the log of e, which is just 1. So it's just going to be 2x at the end of the day. Or you think of these being inverse functions. E to the x and log natural logarithm are inverse functions. So when you do one, then the other, you get just the exponent, just the thing, just whatever you plugged in. And log 3 is something in your calculator. You could plug that in and get a decimal. So log 3 over 2. That's our only potential critical value. So what I can do there, you could plug it in and get a decimal. Again, I don't have my calculator with me because I left the classroom without one, so we'll see if I actually get through this video without one. So that's the only thing that goes into my factor table because that's the only thing that makes something 0. If I look at my function, I have a -1 out front, or my derivative, so I'm looking back at this line. I have a -1 out front of everything. It's always negative. I have e to the -3x. It's an exponential function. Exponential functions are always positive. And then I have e to the 2x minus 3 as my last factor. So I know this is the number that makes that 0. E to the 2x, so basically this number when I plug into the first thing is going to be 3. And I get 3 minus 3, and that's where I get my 0. So I know e to the 2x is going to be bigger than 3 for bigger x values and smaller than 3 for smaller x values. So I'm going to get negative before, positive after. Or again, if you're working with a decimal, just plug in a decimal number before it and plug in a decimal number after it. So overall, our derivative is positive and then negative. And that was a horizontal tangent there. So we have a local max at x equals the log of 3 over 2. All right. Moving right along, so we have this function here. So we're going to get the derivative of it. So it is a logarithmic function, so the derivative is usually 1 over x. We have a function there, so it's 1 over that function. And in front of that x, since our base isn't e, we put the natural log of 3. And I think here is where I'm not going to be able to finish this video without going to get a calculator. So 1 over the function, log of 3 in front, and then the chain rule says multiply by the derivative of that function, which is 2x, and then plus, derivative of x, which is 1. So what I'm going to want to do, I'm going to want to get this as one fraction altogether. So I'm going to turn the 1 into log 3 x squared minus 4x over itself. And that looks a bit scary, but the log of 3 again is just a number. So I have just a number times x squared, just a number times minus 4, and then I have this 2x here. Sorry, there's no x there. That's just a minus 4. So what the top is going to turn into is just some quadratic function. So let's see, Okay, I'm back with my calculator. So the log of 3 is 1.1, it rounds to. So if you keep even 2 decimal places, it would round to 1.10. So what I'm going to do is I'm going to multiply that 1.1 times the x squared and get 1.1 x squared. I have this as my x term, so plus 2x, and then multiply the minus the 1.1 times negative 4 and get minus 4.39 when I keep all my decimal places. So the top turns into that quadratic. And again, I could try and factor that, but I don't want to bother. I'm just going to go to the quadratic formula to figure out where the top is 0. So where the top is 0, should be -2 plus or minus the square root of, now I'm keeping all the decimals in my calculator, so I got 23.31 when I did that without any rounding. So if you use the rounded values, I'm sure you get slightly different in there, but it doesn't really matter. So we're going to get -2 plus that. And -2 minus that. And this one, I lost all my decimals when I was punching that in, so I am using the rounded amount, but the second one that works out to that. So that's where the top is 0. So I can use that in my factor table. We also have to consider where the derivative doesn't exist, which is going to be where that bottom is 0. So it's easy enough to factor x minus 2 and x plus 2. So we get plus or minus 2 as well. So in my factor table, we have -3.1, then -2, and then the next one's going to be 1.29, and then 2. So those are all my intervals. And we have, remember, I just do this full quadratic because it doesn't factor. But I know it's a quadratic that opens up. I know that it's only negative between its two x-intercepts. So something like that. Because again, it looks like that because it opens up. So the negative interval will be the interval between its two x-intercepts. I have the log of 3 on the bottom, which is a positive number. But do keep in mind, like if it was log of something smaller than 1, like log of 0.1 in front, that would be a negative number, so make sure you check that, but log of 3 is positive. And then we have the x minus 2, and we have x plus 2. And we get this one, oh, I'm doing that backwards, switches at 2, and x plus 2 switches at minus 2. I've got the next question written out that I'm bumping into here. So I'm just going to rewrite it down a bit lower. Okay, sorry about that. Now, overall, our derivative is positive, then negative, then positive, then negative, then positive. Now, you would be tempted to say, well, that's a max, this is a min, this is a max, this is a min, so on and so forth. But that's not the case on this function. So I've glazed over something very important, which is that our starting function has a logarithm in it. It is the log of log base 3 of x squared minus 4. Anytime x squared minus 4 is negative, it doesn't exist. The function doesn't exist. So we have to be careful about our domain. So what I would do, if I think about x squared minus 4, its zeros are minus 2 and plus 2. So that's x squared minus 4. So between minus 2 and plus 2, the log base 3 of x squared minus 4 does not exist. So this whole part of my table shouldn't really be there because that's not in the domain of the function. So this value here, the 1.29, is not a max. It's actually not a point on the graph at all. And then minus 2 and plus 2, on those, you get log base 3 of 0. So log base 3 of 0, again, that does not exist. And specifically on a log graph, so that's just like log base 3 of x. that's a vertical asymptote. X equals 0 is a vertical asymptote. So these aren't minimums. They're not points at all. They would actually be vertical asymptotes on our graph. So the only thing we get is that is a maximum right there at x equals negative 3.1 or so. So that's what that one should look like. So figure out where your log graph doesn't exist. So anywhere where the inside function's negative, I block that off my table, and then the boundaries of those areas will actually be vertical asymptotes on your graph. So that's how I handle that. So you got to be careful when there's a logarithm in your function. You got to be careful about the domain. Last one here. The 3 comes down, becomes a 2. The log stays put. And then multiply by the derivative of what's inside, and the derivative of log is 1 over x, so the derivative of log of a function is 1 over that function, and then the chain rule says multiply by that function's derivative after the fact. So what I'm going to do is I'm going to clean that up a bit. So I have a 3, I have log of this great big mess squared, and I have 2x plus 7 on top, and I have x squared plus 7x plus 10 on the bottom. And in fact, why don't we factor that right away and get x plus 5, x plus 2 on the bottom. So there we have it. I'm going to start to keep track of my critical numbers. So critical values. X equals minus 5 makes the derivative not exist. X equals minus 2 makes the derivative not exist. X equals negative 7 over 2. Negative 3.5 makes the derivative 0. And you might be tempted to say that's all, but remember, this can also be 0. So you have to go off to the side somewhere and solve where is this function equal to 0. And logarithms are 0 when their inside is 1. So move that 1 over, you get that thing there. And then that one's not going to factor anymore. So we're going to go to quadratic formula. And we are going to get 2x values out of that. Firing that into your calculator, you should get your two answers of negative 5.3 and x equals negative 1.7. What you're seeing is a very sneaky ninja edit because I actually calculated those wrong the first time and didn't see it until after I was done. But anyway, there we go. So we get that. So we're going to add those. Oh, you can see my wrong answers here. Don't look. Nobody look. We're going to add those to our list of critical values. And I listed them all this time because there's just so many to put on the number line. So you want to make sure you get them in the right order. So minus infinity, minus 5.3, minus 5, minus 3.5, minus 2, minus 1.7, and infinity. I think that's all of them. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we got them all. And then I look back at my function, and we have the number 3 in it, my derivative, I should say. And that number is always positive. We have this log of x squared plus 7x plus 10. Luckily for us that thing is squared. So we know that that's always going to work out to a positive answer. If I had something like that and it was to a power of 3 or a power of 5 or a power of 1, I would be plugging in random values in each interval to see where it's positive or negative. So that would be a lot more work. So luckily it's squared in this one, so we don't have to worry about this. The next factor we have is 2x plus 7. It's going to switch at 3.5. We have x plus 5, which switches at minus 5. And we have x plus 2, which switches at minus 2. Now, same kind of idea as last time, is we need to think about the domain. So I always fill in all my pluses and minuses first, and then scratch out things in the domain after, because I find having the full table there, I can fill out the pluses and minuses faster than having gaps that kind of hurt my brain for whatever. But you can do the step before you filled in your plus or minuses, and then you'll have less to fill in your table. So we have the log of, in our original function, the log of x squared plus 7x plus 10. So anytime this quadratic is negative or 0, that overall function is not going to exist. So that quadratic, its x-intercepts are the minus 5 and the minus 2, because that's the one that actually factors with the plus 10. So those are the x-intercepts of that one. So, and since it, again, it's a quadratic that opens up, it's negative between its x-intercepts. So all of this is not in our domain. And then the boundaries of that domain are going to be vertical asymptotes, because that's where we're doing the log of 0, and that's where you get vertical asymptotes. So we have all of that as not part of our domain. I guess I haven't done my results here. We have our derivative, which is negative and still negative. So negative 5.3 is not a local max or min. I'll just write neither. I don't know why I'm writing. So that's neither, and same deal over here. This is positive and positive. It doesn't change sign, so it is neither a local max nor a local min. So we can say, therefore, no local max slash mins on this graph. And I actually have this up in Desmos, I think, so maybe I'll just show that to you really quick. So there you go. So there's those 2 points, and you can see it's decreasing, flattens, keeps decreasing, so not a local max or min. There's no function at all between minus 5 and minus 2. And then same thing, increasing, flattens, keeps increasing, so it's not a local max or min as well there. Question 2 then says, how would the above problems be different if we gave you an interval instead? If you're given an interval, you wouldn't be doing the factor table at all. You would just be plugging in your key points that you found, so the log 3 over 2 or whatever, and the 2 endpoints, because those will now be in your critical values. So you'd plug all those things in. The biggest answer would be your max on the interval. The smallest answer would be your min on the interval. Remember, you're plugging into the original function on all of them. So that's how that's different. So I think the exit gives you an interval, so you can try it out that way, where you have to plug in, and then the practice that you'll do in class, 3 of them are local max mins, and 1 of them has an interval. So a mix of both types on here.